Ever wondered how some of the most fundamental circuits in electronics achieve their core function, like taking an input signal and scaling it, or flipping its polarity? The answer often lies with the operational amplifier, or op-amp, a remarkably versatile component that is truly the workhorse of analog design. Understanding its behavior and how to analyze its configurations is a cornerstone for any electrical engineer. Deriving the voltage gain of an inverting amplifier involves a systematic approach, relying heavily on the ideal characteristics of the operational amplifier. You will typically follow four essential steps. First, setting up the circuit diagram. Second, applying the ideal op-amp rules. Third, using Kirchhoff's current law at the inverting input node. And finally, algebraically solving for the output-to-input voltage ratio. The power of this derivation comes from understanding the ideal operational amplifier model. This model simplifies analysis by assuming two critical properties. There is no current flowing into the op-amp input terminals, and there is a virtual short circuit between the inverting and non-inverting input terminals. This means the voltage at the inverting input is effectively equal to the voltage at the non-inverting input, which is usually grounded for an inverting configuration. With these ideal conditions in mind, let us walk through the steps. Begin by drawing the inverting amplifier circuit with an input resistor, a feedback resistor, and the op-amp itself. Next, ground the non-inverting input terminal, establishing 0 volts there. Because of the virtual short, the inverting input also assumes a voltage of 0 volts. Now, apply Kirchhoff's current law at the inverting input node. This states that the sum of currents entering this node must equal the sum of currents leaving it. Since no current enters the op-amp input, the current through the input resistor must be equal and opposite to the current flowing through the feedback resistor. To elaborate on the current balance, the input current is calculated as the input voltage minus the inverting input voltage, divided by the input resistor. Similarly, the feedback current is the inverting input voltage minus the output voltage, divided by the feedback resistor. Equating these currents with the inverting input voltage at 0 allows you to directly solve for the ratio of output voltage to input voltage. This ratio, negative feedback resistor divided by input resistor, precisely represents the voltage gain. This elegant derivation showcases the fundamental principle of negative feedback in stabilizing and controlling amplifier gain. By mastering these steps, you gain more than just a formula. You unlock a deeper appreciation for how operational amplifiers are used to precisely control signals. This understanding empowers you to not only analyze existing circuits but also to design your own, knowing exactly how each component contributes to the overall circuit, behavior, and gain characteristic.